In this next screencast, we discuss some of the basic features of graphs of quadratic functions. We'll illustrate these features by looking at the graphs of a few simple quadratic functions. Let's start by looking at example 11.2. Here we consider the function given by the equation f at x equals x squared. Let's look at part A. First of all, how can you tell that this is a quadratic function? What are the values of a, b, and c? Well, if we start by just writing the equation down, notice that we can write x squared as 1 times x squared plus 0 times x plus 0. If I write it in this form, I can compare it to the basic form of a quadratic function, which is a x squared plus bx plus c. And so we can see from this comparison that indeed the function f is a quadratic function. A is the number 1, b is the number 0, and so is c. So let's look at part B. Complete the following input-output table for this function. So we're going to substitute these values here into our function. Well, what is the function going to do to these values? This is a function that squares whatever number you put into the function. So we effectively need to square all of these numbers to get our outputs. So let's do that. 0 squared is 0, negative 1 squared is 1, 1 squared is 1, negative 2 squared is 4, 2 squared is 4, negative 3 squared is 9, 3 squared is 9, negative 4 squared is 16, and 4 squared is also 16. Okay, let's look at part C. Plot the input-output pairs from part B on the axes provided below. Then connect the points with a smooth curve to see what the graph of this function looks like. You should see a curve that is shaped like an upward opening arch. This type of curve is called a parabola. So let's go ahead and plot the input-output pairs that we found on the previous page. We have 0, 0, negative 1, 1, 1, 1, negative 2, 4, 2, 4, negative 3, 9, 3, 9, negative 4, 16, and 4, 16. If we connect the points with a curve, we arrive at a curve that looks something like this. And so indeed you can see that you have a shape that looks like an arch, and this kind of shape is called a parabola. Let's look at part D. Every parabola has a turning point where the trend in the graph changes from downward to upward, or vice versa. For example, in the graph we're seeing above, it starts off with a downward trend and it changes right here and switches to an upward trend. So right here would be that so-called turning point. This point is called the vertex. So at what point is the vertex of the parabola that you drew in part C? So here was that turning point right here, and you can see it's located at the origin at 0, 0. Let's look at part E. On the graph you drew, draw a vertical line straight through the vertex. So let's go ahead and do that. So the vertex is located right here, and if I draw a vertical line straight through it, I get a line that looks like that. So notice that the part of the parabola that lies on the left side of the line is an exact mirror image of the part that lies on the right side of the line. In other words, if we look at this part here on the left side, that is an exact mirror image of what we see on the right side of this line. This is a property that is common to all parabolas and is referred to as symmetry. The line we just drew is referred to as the line of symmetry. So this line right here is called the line of symmetry. Lines of symmetry always run right through the vertex. Okay, now let's look at part F. How many x-intercepts does this function have, and where are these intercepts located? Well, if we look above at our graph, the x-intercepts are the locations where the graph intersects the x-axis. So here is the x-axis, and you can see that the graph intersects the x-axis at exactly one location. So that tells us there is exactly one x-intercept, and that x-intercept is located really at the vertex where the value of x is 0. So how many x-intercepts does this function have? There is exactly one x-intercept, and it is at x equals 0. Now let's have a look at example 11.3. In this example, we consider the quadratic function given by this equation, h at x equaling negative x squared. Part A. How does the value of a for this function compare with the value of a in the last example? Well, in our last example, the function we were considering was f at x equaling x squared. Now this function had an a value of 1. In our current example, h at x equals x squared, which we can write as a negative 1 x squared plus 0 times x plus 0. Now we can compare. This is ax squared plus bx plus c. And so we can see that in this case a is negative 1. So in the case of h at x, we have a equaling negative 1. So how do the a values compare? They are opposite in sign. 1, negative 1. So the a values are opposite signs. Let's look at part B. Complete the following input-output table for this function. First of all, there's a little mistake here. This should be h. h at x, not f at x. Okay, so we want to substitute 0 into this function, and when we do that we will get an output of 0. Next we substitute -1 into the function. So if I substitute -1 into this function, the function squares -1 and then negates it. When you square -1, you arrive at 1, and then you negate it and you get a -1. So the output is a -1. When you substitute 1 into this function, the function squares 1 and then negates it. 1 squared is 1, so you arrive at -1. Applying the same logic to the other inputs, you arrive at outputs of -4, -4, -9, -9, -16, and -16. Okay, let's have a look at part C. The axes below show the graph of f at x equals x squared, which you plotted in the previous example. On these axes, plot the input-output pairs for the function h at x from part B. Then connect the points with a smooth curve to see what the graph of this function looks like. You should see a downward opening parabola this time. So let's go ahead and do this. Our input-output pairs from the previous page were 0, 0, so that's this point right here, -1, -1, which should be about here, 1, -1, -2, -4, 2, -4, -3, -9, should be about here, 3, -9, which should be here, and -4, -16, and 4, -16. Now if we connect these points with a smooth curve, it looks something like this. So in fact, we do see a downward opening arch, or a downward opening parabola. So notice here that the upward opening parabola corresponded to an a value of 1, and the downward opening parabola corresponded to an a value of -1. So let's have a look at the next part here, part D. Make a conjecture, in other words an educated guess, about how the sign of the number a affects the appearance of a parabola. Well, one guess that you might make is that if a is a positive number, like 1, the parabola opens upward, and if a is -1, or is a negative number, the parabola opens downward. That would be a very reasonable conjecture based on what we've seen. So let's write that down. So if a is positive, then parabola opens upward. And if a is negative or less than 0, then parabola opens downward. Okay, let's continue on. Let's look at example 11.4. Consider the function given by the equation g at x equals x minus 2 times x plus 4. Let's look at part A. This is a quadratic function. How can you tell, and what are the values of a, b, and c? Well, let's rewrite this function. We have g at x equaling x minus 2 times x plus 4. Well, first of all, notice that this function is a product of two linear functions. Notice this is linear, that is a linear function, and this is also linear. And one of the things we said in our earlier screencast is that quadratic functions are formed by multiplying together two linear functions. So that's one way we can tell that this is a quadratic function. Another way we can tell that this is a quadratic function is by multiplying out these two linear factors. We can use the distributive property to actually multiply this out. Remember, each term from the first expression has to multiply each term from the second expression. So let's multiply these two expressions. X times x gives us x squared. Then we can multiply x by 4 and get 4x. Then we can multiply the negative 2 by x. That will give us a negative 2x. And then we can multiply the negative 2 by a 4 and get a negative 8. Now, if we simplify by combining like terms, and those two are like, we see we get x squared plus 2x minus 8, which we could also write as 1 times x squared plus 2x minus 8. So you can see from here that the equation, that the function has the form a x squared plus bx plus c. So here a is 1, b is 2, and c is negative 8. So it really is a quadratic function. Okay, let's have a look at part B. Complete the following input-output table for this function. Okay, first of all, again, there's a mistake here. This function's name was g, so we want to put a g there. Scroll up a little bit to give us some more room here. Okay, so we want to substitute negative 5 into the g function. One of the things I want to illustrate to you is that we have two equivalent formulas for the g function. We have this version, where we have a linear function times a linear function, and then we have this version, the ax squared plus bx plus c version. They are equivalent to each other. You can use either version to calculate outputs of this function. So let me illustrate this point. Suppose we substitute negative 5 into this function. So I take g and I substitute negative 5 in. If I use this version of the equation, then I would substitute negative 5 in as follows. It would be negative 5 minus 2, negative 5 plus 4. Now let's simplify. Negative 5 minus 2 is a negative 7. Negative 5 plus 4, make that look more like a 4. Negative 5 plus 4 is a negative 1. When you multiply, you arrive at an output of 7. Alternatively, we could have calculated the output by substituting negative 5 into our other version of the quadratic function. Let's try that. So if I substitute negative 5 into that version, I would take negative 5 and square it. Then I would add 2 times negative 5, and then subtract 8. Now let's simplify. Negative 5 squared is 25. This is a negative 10. So when we simplify, we have 25 minus 10 minus 8. 25 minus 10 is 15. Then we subtract 8, and notice we arrive at 7. So we arrive at the same output regardless of whether we use this version of the function to arrive at our outputs or this version. You can always use either version of the function. So when we put negative 5 in, we get 7 coming out. Similarly, you can calculate all of the other outputs from substituting these input values in. You will arrive at a 0, a negative 5, a negative 8, negative 9, negative 8, negative 5, 0, and 7. Okay, let's have a look at part C. Plot the input-output pairs from part B on the axes below. Connect the points with a smooth curve to see what the graph of this function looks like. Okay, well, if we use the input-output table from the previous page to plot points, we see we have a point at negative 5, 7, which is about here, negative 4, 0, negative 3, negative 5, which is about here, negative 2, negative 8, negative 1, negative 9, 0, negative 8, 1, negative 5, 2, 0, and 3, 7. And again, if we connect these points with a smooth curve, we see we arrive at a graph that again has this arch shape. Again, it's a parabola. All right, let's have a look at part D. Is the parabola opening upward or downward? And how could you have guessed the answer to this question simply by looking at the equation of the function? So if we look at the graph of this function, clearly it is upward opening. Now how could we have predicted this? Well, the equation for this function was g at x equals x squared plus 2x minus 8. What was the a value for this? Well, you can see the number in front of x squared must be 1. A is 1 for this function. And we made a conjecture shortly ago that if a is positive, the parabola opens upward. So that agrees with what we're observing here. So since a is positive here, the parabola ought to open upward. Let's look at the next part. where is the vertex of this parabola located? Remember, a vertex is the turning point. This parabola has a downward trend, and then it changes right here and switches to an upward trend. The turning point is the vertex, and that is located right down here. And notice it's the lowest spot on the vertex, and it occurs at the point -1, -9. So that is the vertex. Part F. How many x-intercepts are there, and where are they located? Again, x-intercepts are the values of x where the graph intersects the x-axis. You can see from looking at the graph that the graph intersects the x-axis in exactly 2 locations. So there are 2 x-intercepts. One of them is located at x equals -4. The other is located at x equals 2. So there are exactly 2 x-intercepts, and they are located at x equals -4 and at x equals 2. Okay, let's have a look at our next example, 11.5. Draw parabolas that fit the following descriptions. So at this point, you should go ahead and pause this recording and work the parts of this exercise on your own, and then continue playing the recording to see the parts worked out. Okay, let's go ahead and work the different parts of this example, beginning with part A. Draw a parabola that opens downward and has 2 horizontal intercepts. So we can start by drawing some axes. So here's a vertical axis, here's a horizontal axis. Now we want a parabola that opens downward, so it has to have a basic shape like this, and it has to cross the horizontal axis in 2 places so that we have 2 horizontal intercepts. So a graph that would accomplish that might look something like this. It's downward opening, and it hits the horizontal axis in 2 locations. Okay, now let's look at part B. Now we want to draw a parabola that opens upward and has no horizontal intercepts. So again, we begin by drawing some axes. This time we want a parabola that opens upward, so it has to have that basic shape. It must have no horizontal intercepts, which means that it cannot cross the horizontal axis anywhere. The whole graph has to lie, therefore, probably above the axis. So a graph like that would accomplish what we're looking for. It's upward opening, and it never hits the horizontal axis. Let's look at part C. Now we want to draw a parabola that opens downward and has a single horizontal intercept. So again, let's begin by drawing some axes. The parabola we want to draw this time opens downward, so it has to look like this, and it has to cross the horizontal axis in exactly 1 spot. Well, the only way this could be accomplished is if the vertex of the parabola, that's the turning point, if the vertex lies right on the horizontal axis. So there's that turning point right there, and it's right on the axis. So you can see parabola opens downward, and it hits the horizontal axis at exactly one place, namely at the vertex. Okay. So we close this screencast by summarizing the graphical properties of quadratic functions that we have observed. So consider a quadratic function that is given by this equation, f at x equaling ax squared plus bx plus c. First of all, the graph will either be an upward or downward opening parabola. If a is positive, and remember a is the number in front of x squared, if a is positive, then the parabola opens upward. If a is negative or less than 0, the parabola opens downward. Next, the graph can have 0, 1, or 2 horizontal intercepts. We've seen that in our last example. A parabola can hit a horizontal axis, in other words, in either 2 places, 1 spot, or not at all. Next, the graph will have 1 vertex, in other words, 1 turning point, and that vertex represents either the highest or the lowest point on the graph. To illustrate, if you had a downward opening parabola, notice the vertex represents the highest point, but if you had an upward opening parabola, the vertex represents the lowest point on the graph. Finally, the graph of a parabola will be symmetric about the vertical line drawn through the vertex. So if I draw a vertical line straight through the vertex, the part of the graph that lies on the left will always be a mirror image of the part that lies on the right. So this summarizes the basic properties that we've observed in this screencast with the examples.